We'll have our first talk of the afternoon by Arun, and this will be her second talk, and we'll have the first problem section for our course at I think 4:20 by Daniel, which will be in this room. So change of plan so that we can all sit in the same place. The problem session will be in this room. And we have two method problems, so that will be easier, but there's also room to like room and assistance. I also posted the links on the website, so you can either go to the website or just write down those URLs and see the questions. Thanks. All right, thank you for returning. Anyone have any questions for the morning that we should address before we get started? There are a couple of questions that came up in the discussion that I want to talk about in a second. If you have other questions, please bring them later, go to the TA session, and so on. First question that someone asked, that was, someone asked, when will the Lecture2 lecture notes be available? I will probably type them during Mark's lecture. So they will be available then. I will also be paying lots of attention. I'm sorry that I didn't have very much time to go into more historical context about the distant emitting theorem. More on that is already typed out in the lecture notes, and I'm very happy to talk about this more, but in fact, maybe you shouldn't ask me because I won't stop talking about it. So you can talk to other people about it. I just wanted to remind you of the picture. The input has both F and G. You can't work with just F on its own. F needs a friend. And one way to think about that, for example, is if the friend were not needed, then every knot would be sliced, which you know it isn't. So there are some nice examples to keep in mind of like the G really is very important. And then, right, so the input has these two pieces, both an F that you're going to embed and the friend that's going to help you do it. And the outcome has two pieces as well. You're going to embed F, make it an F bar, which is locally flat embedded. And then it's going to come with a G bar, which is now geometrically dual rather than just algebraically dual, like it was before. One question that came up during the discussion a couple of times, so I wanted to make sure to mention it. There were a lot of questions about what did I mean by these self-intersection numbers. There are a lot of different versions of this, like 3 different things we might be talking about, and they're all kind of, they're not identical, but they're related. So I was always talking about, you know, take these signed points, they're signed because I'm in a simply connected manifold, everything's orientable, and you're just, I just meant count these up. Okay, that's what I meant. But there's a couple of other things that we could have meant. So I wanted to write down this sort of wonderful formula that relates these things. So let me first write down the formula and then we'll talk about what I mean by this. Let me write it for G, because it's easier. So in this simply connected setting, there's this nice formula relating these different notions. I'll tell you what these are in a second. This E, this mu of G is the normal bundle of G. It's worth thinking about, what do I mean when I say normal bundle of an immersion? It's what you think it means, but you should figure out what you think it means. But there is a normal bundle and it has an Euler number. So that's what I mean by this. And in particular, if G is embedded, it's the Euler number. This thing over here is what I was referring to in these theorem statements. It's a signed count of like just, I'm not taking any push-offs, I'm just looking at these intersections, counting them up by sign. That's what that is. And then this you could consider a signed count. This would be a signed count of like G intersecting a push-off of G. So you could take G, push it off on the intersections. That's one way to think about it. But I would rather call this the homological intersection. which is just G is a class in H2. So I could like take its concrete duals, cut them together, evaluate fundamental class, that sort of thing. That's what occurs here. They're all related, but they're not identical. In particular, you could consider the CP1 and CP2 is embedded, but has a non-trivial normal bundle. So they're like, that one's 1, this one's 0, the homological thing is 1. And so you can have all different constellations of these arising. I was talking about this one, not these ones, but these things do also come up. So in particular, when I said this G has a trivial normal bundle, I meant this other number is trivial. And then I said it has trivial self-intersection. So in particular, that implies the homological thing. But it's not like, they're not all equivalent.
So when you isotope G to G bar, you are not changing the left-hand side, but you guarantee the right-hand side to be unchanged?
This G?
Yeah, when you isotope to G bar.
I'm homotoping the G as well.
Oh.
So G and G bar are homotopic. They're in the same homotopy class.
Yes.
But they're not isotopic in general.
Yeah, sorry. Yeah, I mean, can you guarantee the normal bundle of G bar to be real generally?
I think so. That's right. I think in fact they will be regular. But I was trying not to use that phrase. But in general, yes, they will all be regular. Well, F will not be regularly homotopic to F bar in this group, but G and G bar will be regular. All right. My plan is to do the proof of the theorem. Let's get started. Okay, so here's the theorem. So again, reminder. I'll have an ambient core manifold that's closed. I'll have alpha inside of H2. That's primitive. And now represented by a locally flat embedded box. Okay, step 0. Let me be quick about the first few steps. I know that this was simply connected, which I forgot to write, sorry. So I was working in a simply connected form manifold, simply connected space. So by the heritage theorem, this came up last lecture as well. Pi 2 is the same as H2. And in particular, this means that alpha is represented by a class of some S2 mapping into my M4. I'm using the definition of pi 2 here. It means that there's a map from S2 to M4 representing my class. And I'm going to use my immersion lemma, which I had before. It says that I can assume that it's a generic immersion. But it's not just a scary continuous map. It's a very nice function with these very nicely controlled isolated double point singularities. Here's where the primitivity will come in. So alpha is primitive. I can use Poincare duality to find some beta given by up to homotopy, some map of S2 going into M4, such that alpha intersect beta is 1. It's the only place where primitivity will come in. You know what I'm talking about? Poincare duality, closed manifold, non-singular pairing. Okay, everyone happy so far? And once again, I use the fact, well, usually that would have been an H2, but that's pi 2, and then immersion lemma. So very nice. This is something I've written on the level of classes, but I can interpret that now also in terms of these representatives. So what this condition means is that F and G are algebraically dual, right? So in particular, this means that F and G are algebraically dual. which means that if you do the sign count thing, f dot g will be the same as the homological thing. So I could use this lambda if I wanted. This is going to be 1. This is the German way of writing ones. Sorry if it looks like a 7. All right. Now I'm going to do an annoying thing. I'm going to black box something that's in the exercises. Okay, so my apologies for that. It would just take me too long to go into it right now. There's something called the geometric passive lemma. It says that up to homotopy, and assume that f and g are geometrically dual. As a reminder, this meant that they intersect in a single point. You should be annoyed with me. It seems like, wait, am I not just done? What's going on? There's a price to pay that f and g might become more immersed when you do this process. So this is saying you might start off like in this picture, the left and right, they're algebraically paired up nicely. So you can make it actually paired geometrically nicely, but each thing will become more intersecting when you do this. Okay, yeah.
So to use casting, you need G to at least have an even framing, and I don't see how you got that yet.
You don't need that.
Don't need.
It's in the black box that you will solve in the TA session. I promise. Daniel will tell you all about it.
Okay.
But I promise you don't need it. Okay. And I'm also happy to talk to you more about this later. There's some gadget, also very direct hands-on methods, which will give you a homotopy, which will make this out geometrically dual, but f and g will become more immersed. We'll do this second annoying thing. We're going to keep calling them f and g. Okay. Is there another question? Did I see? Yeah.
Do we not know that they were algebraically dual from the hypotheses? Or
They were algebraically dual, and now we're getting that they're geometric.
oh, okay.
Meaning that the intersection is actually a single point. So I wanted to show you what the picture looks like right now. So here is our current state. Our current state might look like this. This is, oh no, this beautiful chalk, oh no, sorry. Oh, thanks. So this is my current state. Do you believe that? I just drew one because why not? So there's some self-intersections, but they intersect each other geometrically. All right, now we get to the actual step 1. So this was all step 0, so step 1. We're going to modify F so that the self-intersection of F is 0. And if in case you're keeping track, I mean the signed count of self-intersections of F. And the procedure for doing this will be something called interior twisting. So this will be the first of our very explicit direct hands-on methods. And it will look as follows. F is a locally flat generic immersion. As in most places, it looks super nice, except for these double point singularities. So here's a little bit of F. When I've drawn these pictures, I mean, it's a movie picture of like, these are different R3 slices. And these red lines are giving you a little patch of F. My modification is as follows. In these Yeah,
This F dot F, that should not be on the right intersection,
that was the signed count of intersections.
just the same count.
That's right. So here I've drawn, suggestively, I've drawn it so that it's not 0. Explicitly, it's just 1. And in your mind, you know what you want to do. You just want to add a little doohickey, which will have a minus on it instead of a plus, right? That's what your heart wants to do right now. And that picture is telling you that you can do it. So it's the explicit way of adding a little doohickey, little teeny tiny self-intersection. That's the explicit way of doing that. This makes sense. Have I lost everyone? Thank you. Yes.
I'm a little confused how to read this picture because the last time we saw a bunch of lines changing with respect to time, we were thinking of it as a plane.
Mhm.
So is this a? Oh yeah, well I get it. Okay, I answered my own question.
That's great.
Sorry.
You want to answer it for everyone else?
I don't think I can.
Okay. So
I have like vibes, but not words.
I think here's what the vibes maybe mean, hopefully. So earlier we were talking about planes, right? We were thinking of how to think of the ZT plane inside of R4 by drawing these R4 slices, R3 slices. But when I say that F is, like right here, F is locally flat. In all of these points except there, F is locally flat. So that means there's a little patch of R4. Inside of M, there's a little area, which is homeomorphic to R4, such that under that homeomorphism, F goes to one of these coordinate two-dimensional planes, right? And so in particular, this thing where I've now drawn out these slices, these vertical lines, when I sew them together, will be a little patch on F. And it's just a very innocuous, somewhere over here, don't care where, just not there. Anywhere else will work. Your surface looks like this. I'm going to do this very small local modification, which is this twisting. In the middle, you see this point of intersection. But that's just an isotopy inside each individual R3 slice. So this is a little thing. This defines some like band-aid that you can remove this from the surface and put that in. You can surgically implant this into your F. And what that might look like is something like this. Let me do that there. So I've surgically implanted that little -1 in there. You might ask, well, is that -1 or +1? And I've never figured it out. It depends on whether you twist it this way or that way. And one of them is plus and one of them is minus. Do the right one. Yeah?
How do you know that just doing 1 minus 1 doesn't mean you to do more -1 to receive +1? In other words, why you guarantee that just doing 1 in don't fix it? Or
Because I'm doing just assigned count, right? So the thing you should believe, the thing I'm trying to convince you of, is that this implantation is possible. And the reason it's possible is because that on the edges of this square, they're the same, right? Like on the two ends, I have these nice vertical lines. The top and the bottom I haven't changed. It's only the inside that I've changed. So I've removed a little square and I've put in a little square. So I've done a totally local modification. So the thing that you should believe is that that is possible. Do you believe that? Maybe, so, yeah. But once you believe that I can do this local modification, well, now I have.
yeah, once you can do that, yes.
Yeah, okay. But once, I mean, I've added in a little extra intersection. Something that Mark and I agreed earlier is that you can always make things worse. You've just made things worse. You should be asking yourselves, like, why would I want to make it worse? And this is telling you, you can always make it worse. Make it more badly behaved.
Too bad is makes it too good.
It's the Friedman, no, I'm just kidding. Yes.
And there's no way to kind of cheat and go back and actually get rid of it with the, there's not sign, just actually get rid of this thing by going, just doing the opposite thing. So,
You can't do the opposite thing, right? Like it's like that is super nice and local, but the actual thing you might have in your for space could be like pretty weird. And so you can add an extra one, but when you do that, like implant, you can like try to remove something and put it back. If you're very lucky and you happen to know it looks exactly like that, then yes. But do you?
so you see,
And it's clear there from a topic, so it's the same homology.
That's right. Same homology class, same homotopy class. Very local, teeny tiny maneuver. Seems to make it worse at first class. But you know, we are doing it with a purpose. It will help us in the end. And one reason to think about why it's going to help us is like, we're hoping to change this F to an embedding. And like an embedding has sign count of intersection 0. And so you're kind of trying to like algebraically match the geometric thing you're aiming for. And like, you know, this is the first step. Yeah?
Do you know a picture for a more complicated self-intersection?
I think a more complicated self-intersection wouldn't necessarily live in an R4, right? And so I'm not saying that this is what all self-intersections look like. I'm saying like you can always add in things that look like this. Does that help? So I'm refusing to answer your question, is what's happening.
Okay.
That's right. But there can be self-intersections that look much more complicated. And in particular, this is kind of a cartoon picture. Like I could take a point of intersection and more generally, that little loop that you can sort of see could be non-trivial in pi1. Obviously, I'm working in a simply connected setting right now, but in general, there could be non-trivial pi1 elements associated with this. And that things can get much more complicated.
Which will look like? That's not an actual blueprint, right? So
Well, whenever you have a self-intersection, so like that F is some map of S2. So whenever you have a self-intersection, you have some P1 and P2 mapping there. And the loop that I'm both P1 and P2 map to some point. And there's a loop, namely, take any path connecting these two and see where it goes. And potentially that could go to a non-trivial element in pi1 of your format. Not here, something connected, but in general, sure. And so if you're trying to draw the most general self-intersection, you have to sort of keep track of all sorts of possibilities. They will not all look like this. You can try to convince yourself that if the pi1 element is trivial, then it will look like this. You still have to be very careful about like, why should your null homotopy be like this super tiny, teeny tiny disk? It's not obvious. How are we doing? Who's happy, who's sad?
You could always eliminate every self-intersection, and you could just represent everything by an embedded sphere.
Right, so you can't remove everything. Mark's question, I think, was more like, why can't you? And I was hopefully helping with that. Who's happy and who's sad? Thank you, thank you. Any sad people? Tell me more.
Even if the manifold itself is simply connected, the complement of the curve manifold, so it's not clear.
That's a great one. So to repeat that, even if a manifold is simply connected, the complement of a given embedding or immersion does not have to be simply connected. So in this super nice situation, you get an honest to God embedded little tiny disk in the complement of everything. But even in a simply connected manifold, that's not clear why you should always get that. Tell me more. What makes you sad in this context?
so. Yeah, so you said it represents the same like homology class, but you're adding you're trying to get rid of this intersection, but the homology class has a given self-intersection of itself.
That's a great point. Here's what I was doing.
Mhm.
I fixed a homology class. This is what Gardner was saying. I definitely changed the sign count.
Yeah.
So in order for that to stay the same, this one better be canceling it out.
Mhm.
And that is another one of the homeworks that you will do in your problem session. Daniel will tell you so much more about that. But that's a great point. So you should be worried about this, but in fact, it does work out. And if you believe, there are two ways of doing this. You could try to prove this formula, and then once you believe the formula, you'll know that the Euler number changes in precisely the right way. Or you can look at this picture and try to figure out, how does the Euler number change? And I claim that all of you will draw these beautiful pictures, which will show you that the Euler number changes by precisely the right number. It will be plus or minus 2, depending on whether that's plus or minus 1, which are you slightly less? I'm gonna carry on because I haven't made any headway.
When you write the total, that means that you see, sign up one.
That's right. That's right. I wasn't sure whether I should use that notation or not. So I was thinking this might be simpler, but yeah, I mean this. So sign count is 0. But lambda is homological, mu is regular homotopy invariant, if that means something to you. Okay. All right, so now I'm in this situation. And then, what do I know? As you just pointed out, I could look at look at my points of intersection of F with itself. They're paired up now in pluses and minuses. So I can split them up into like each plus gets a friendly minus, sort of like I have in this picture. And then I can consider a circle that's going between them. It's very similar to what I drew over here. There's, for each double point, you get a circle like this, but now you have 2 double points. So you have like 2 arcs that fit together to give you a circle. I hope that's clear from the picture. In fact, I like to do it here. So now in my current state, I notice that the points in the self-intersections of F with itself can be paired by circles. But we're in a simply connected four manifold, as I conveniently erased. So these are null homotopic. Just an M, my big ambient four manifold. So they'll look something like this.
We know what's up in the ambient.
Yes, in the big manifold one. That's the only one that I know is simply connected, as you pointed out. So in particular, I have some map of a disk with that circle as a boundary. That disk can be assumed to be generically immersed, which is what we said earlier. It's something we're allowed to do. We can assume that disk hits everything nicely transversely. Another thing we said that we can do topologically. So I can assume that there are these points of intersections only, so they don't intersect too badly, but they do intersect. Okay, so I've tried to draw a very generic picture over there. And so because of these null homotopes, what I get are what I'll call W's. These are generically immersed disks in M. And I'm going to say what you want to be true about them. So here's your dream sequence. So in the nicest of all possible worlds, here's what you would have. You would have F intersecting F like this. There'd be this nicely embedded disk right here, the interior and the complement of everything that has happened so far. And the reason you want this to be true is, well, you look at this disk, you sort of push it off of itself to get 2 copies of the disk, and you use that as a guide to like modify this flat sheet of your surface F so that it no longer has those intersections. That's very confusing if you haven't heard that before. What I mean is, I'm going to remove this flat bit in this flat sheet of F, and I'm going to put on a little hat guided by this green disk, like this. So this hat has like a front portion and a back portion, and they're both like parallel copies of the original green disk. Kind of looks like a tea cozy that you've put on top of your surface. This flat rectangular bit is no longer there. That's where the intersections were though. So you remove those 2 intersections. So if your dreams could come true, this is what you would have. This thing that I've just shown you, this is called the wiki. Me have a show of hands of who has seen the Whitney move before. Not everyone, but many people. Thank you. So if you haven't seen this before, it's a great thing to go look up. It's one of the, if I could rank all of the best moves in topology, this would be up, top 5 for sure. So very important move. If you haven't seen this before, please do look it up. Questions? Some of those hands were questions. Yes.
When we choose the arcs that pair up the intersection points, are we doing so in a way that, like, are we trying to not pass through the intersection of G?
So
do we care?
The intersection with G does not matter, but you can always choose such an arc.
Oh,
right?
yeah, sorry.
But that's
Okay.
a good question. You should worry about this. In the intersection with G, we can just sort of slightly move it off to the side, and then it will be fine because the intersection with G is a single point. But that is something that you should do. You shouldn't not do it. Does that make sense?
Yeah.
You should do it, and you can do it. So do it. Other questions?
Please, you can repeat what you said. What did you mean?
So the initial picture was I was drawing F in 2 different ways. There was a flat sheet and this line sheet. And of course, now that you've seen our 2D pictures from before, this line sheet is moving back and forth in time to get the actual surface. In a nice situation, there would be a green embedded with disk W, which looks just like it does in this picture. Okay. And if I have that situation, then I could remove this little rectangular portion in the flat sheet and replace it by 2 pushed off copies of the Whitney disk W and a little strip. So in my mind, that looks like a tea cozy. You might consider it an igloo prison, various ways of thinking about this. But it's like this little thingy you put on top to sort of fill in this gap. If you prefer, you could think about isotoping the F along the W, like this. But the end result is that the new F no longer has those 2 points of self-intersection.
So the green is that it appears in this way.
That's right.
As opposed to
The reality. The reality, unfortunately, looks like this. there's all sorts of problems that can occur. What are some problems that can occur? Well, first of all, came up earlier, all I knew was my null homotopes were in M. So in particular, I could have self-intersections with F, right? Other problems is W as a null homotopy doesn't have to be embedded. So it could have these self-intersections like that. You were talking about arcs earlier. Kind of said, like, I just drew one with disk. Maybe there's like 20. Maybe they're like, maybe those intersect one another. And then finally, did this when I made my T-cozy, I did this push off. Whenever I do push offs, I'm using something called framing. Framings are always confusing. The framing might be wrong. So I might in fact have the wrong framing. Something like this. So this is my reality. It's sad. What we'll do in a moment is say, how do we fix it? How do we start with this and get here? Because once we're here, we'd be done, right? So we are sad but stoic. It's like, okay, fine, this is what we got, but we fix it. And then we win. That's roughly the rest of the proof. We'll actually do it. Question?
And what about intersections with G?
We will also avoid those. You're absolutely right that there could be intersections with G, but we don't need to avoid it because in the theorem that is here in your mind, I don't need the G actually, right? Because all I was trying to do was embed that. The G will be very helpful in going from the reality to the dream. But once G has helped us, we will be mean and just throw it away. So if my eventual F intersects with G, that's fine.
You were claiming that the final F bar and G bar are geometric intersections.
I am not, because that was the disk embedding theorem. I'm not proving that. I'm proving a totally different other.
Yes.
We're very similar, so very confused. Other questions? Yes.
Here you only have two intersection points in this picture, but if you have more, like, should I be worried about the choice of which one we're getting that, or is that not going to be?
What you have to make sure is that there's some pairing for which you can achieve your dream. And the dream, I've only said this situation with one. What am I trying to say? If you had two K intersection points, then I'd have W1 through WK, and I would want all of them to be embedded but also disjoint. And so in some sense, I'm including that in these fish. So, it was supposed to be intersections of W with itself, but it could also be W with some other W. You also want to avoid that. So it's true that, but like changing the pairing up of the intersection points is something you have the freedom to do. So as long as there's some pairing which achieves your dream, you'll be done. I won't really talk about the pairing today, but it shows up in like the weeds of the proof. But that's a great question. Yeah. Other questions? Have 5 minutes. That will not work. We did start 5 minutes late. Can I steal those 5 minutes back? Is that it? Thank you.
I'll give you 5 minutes.
Thanks, Mark. So generous. Maybe I'll listen to your talk. Phone is telling me there will be 5 minutes. What is a good way to proceed? Okay. Great. So I'm going to write down problems. First problem was that the interiors of my Whitney disks might intersect. That was a problem. My second problem was this twisting. Didn't define this, but don't have time. We'll talk about it later if you would like. This is the framing obstruction. Okay. So this will be something in the integers. So let me just say it out loud. I have these Whitney disks. These are generically immersed. So they have a normal bundle, but it's a D2, so it has a trivial normal bundle. So you look at that trivial normal bundle and you restrict it to its boundary, and that gives you something on this circle. On the other hand, in order to do this Whitney move, you need the correct framing. And that's a framing that's going to be tangent along this flat sheet and normal along this vertical sheet. So that's a different framing of a D2 bundle over that circle. You compare those two. They might be the same, in which case that twisting number would be 0, but they might not be. So that's some integer that you have to be careful about. That's what I'm calling the twisting number. I'll put an actual definition in the notes. This will be a good defense mechanism for myself to just say that. Due to poor planning, I'll write the rest of the problems here in a different medium. So the third problem is this boundary intersections. And then the final one is these interiors of the Whitney disks might intersect my original surface. So in the middle here, so I wrote down problems, but that's so mean. Also write down solutions. But unfortunately, solutions come with a cost. So we'll also have to pay them. And I want to give you some examples of what I mean by this. So the easiest solution I can give you is for these. This is to tube into G. So what do I mean by this? Well, I've arranged for F and G to be geometrically equal. So G intersects F at a single point. And let me abuse my privileges as the person drawing. Draw it right here. That's my G. And I could just take my W. So W was mostly here, right, in my big reality picture. And I could just like add a little tube, add on a little copy of G. It got worse. It has more fishy because like it has all of these self-intersections of G became self-intersections of W. But the intersection with F got fixed. In fact, we can very carefully keep track of the precise cost. So let me write that down. You have the intersections with F, they go down by 1. That's the good thing, we really like that. But the twisting number of whatever Whitney disk you're working on, this changes by the Euler number of the normal bundle of the G, right? And then we have no idea the interior intersections of WI with itself, these can change arbitrarily. That's like quite a big price to pay. You decrease this, you change this by a known amount, and this one becomes totally wild. Okay? But that is a very explicit geometric thing that you can do.
So WI with itself, but you wrote WJ.
The reason it can be WJ is because you're going to use the G multiple times, right? And so you might do it for this W, but then also for some other W eventually. So this one will change W self-intersections, but the moment you have two Whitney disks that you're doing it to, you'll also change the mixed intersections as well.
Other Whitney disks might just intersect G.
Sorry?
Other Whitney disks might just intersect G. So
That's also a great thing. So you may well have greens intersecting here. So, thank you. Other questions? I'm going to erase the dream, which is a bit sad. Let me draw you this one. It's called boundary push-off. Looks like this.
Why would we have boundary intersections in the first one?
Yeah, you could be clever and choose them to not intersect, but I want to consider it for a future reason. But it's a good point. So suppose you have a situation where they actually do intersect. It's a weird picture, okay? So there's a flat F. And there are two arc Fs. And they have green boundaries. They intersect like this. Is it making sense? Thank you. Thank you. Nodders. Thank you, sir. It's very helpful. I want to get rid of that point of intersection. You're imagining this top green disc like right here, right? Roughly, I mean, it has problems, but it kind of is there. So we're going to like poke out a little finger and push that green in this direction all the way until it like no longer has that intersection. So I'm just going to delete this little section and then just move it like this. But when I do this, I can't like leave the disc behind. I don't know, you guys might be too young for this. I'm imagining like some Looney Tunes cartoons, like the mole is underground. You see the little tunnel above him. So there's like that sort of tunnel above this guy too, right? There's like this little thing. Yeah. There's an intersection with F right there. You see that? So this one was an F. And so what I'm saying is that that boundary push-off, it decreases my intersections. These intersections get a -1. You can do this to self-intersections as well. But when you do this, you increase the intersection of WI with an F by precisely 1. Yeah, that makes sense? The picture makes sense, roughly. Now, I will tell you something about those two problems in a second, but let's look at these two. What I want you to take away from this is that when we first started with this reality, these problems may have looked orthogonal to one another, right? There's this problem and that problem and that problem, and you have to solve all of them. But what these moves are telling us is that they're related, right? Like, for example, this is a problem. I can fix it by creating this problem. In fact, this only had that price, so I can solve all of this problem by making this one worse. This one, well, I can remove those problems by tubing, but that changes these problems. Do you see what I'm saying? Yeah? So these are not orthogonal. I don't have like 4 times integers worth of problems, or 4 times 85 integers worth of problems. They're actually all related. Now I know I'm testing your patience. Here we know already something. This one, we already saw interior twisting, which was the first implantation thing that I showed you earlier, which allows you to add these extra intersections. I'm feeling that actually helps you solve the twisting problem as well. This is part of your exercises, as you may have expected. This, where did it go? We agreed earlier that will change that twisting number by plus or minus 2. We didn't really agree. We were earlier talking about Euler numbers. The Euler number and twisting number are kind of the same. So it changes this, but it also adds self-intersections of these guys. So it creates more of the first problem. But in particular, if your twisting number was even, you can do this procedure to change everything into this first set of problems. And then there's one other operation here that one can do, which is called boundary twisting. I meant to draw the picture, but I clearly don't have time. But let me just write down what it does. This allows you to change the twisting number by plus or minus 1. But you pay a different kind of price. The intersection between a W and an F goes up by 1. So you can use this procedure if you want to change it by multiples of 2 and pay this price. Or you can use this procedure to change it by any integer you wish for. That would be sufficient, but then you have to pay that price. Okay. I'm going to say 2 things and then end. Thank you so much for being so patient. Let me write this down over here. The first thing is a black box that I'll talk about let's black box this for now. And I'll talk about it in lecture 3. We'll begin with that. Here, the solution is the disk embedding theorem. I'll tell you more about this later, but in particular, this says that if you have Wi with all the other problems solved, so with the twisting number 0, the interiors with F not intersecting, and then the boundaries disjoint and embedded. Then you can find embedded Whitney disks. I'll tell you more about this later. In particular, where do you find the dual sphere? They'll come from Clifford tori. We'll talk about this. Now, basically what this is saying is, if you can solve all of these remaining problems and push everything into this, then you can apply the disk embedding theorem to get actual embedded Whitney disks in the complement. Then you have succeeded to find your dream. Then you could do your Whitney move, and then you would be done. And then what we do is we look at this table and we see, okay, I'm going to play a game. I'm going to fix these, make these problems, fix these, make these problems, and then try to do it in a clever way in the right order. Okay, so in particular, first thing you do is fix these. The only thing that messes up is this one, So you've just gotten rid of problem 3. No more problem 3. Now you're in problem 4. Well, you can do this. Do these to get rid of all of these. These ones are free now, right? Because I don't care about these. Disk embedding theorem will cure all of those. So these ones are basically just, I can spend as many of them as I want. Now the problem is this. This Euler number is even, then I win. Even Euler number, interior twisting, changes this, don't care. Disk embedding theorem, you win. Odd Euler number, want to do this, wrong price. You're stuck with the same problem you were solving. You get stuck in a loop. Don't win. So the upshot of this table is that there is a Z2 obstruction. That Z2 obstruction is precisely that Euler number. That Euler number where even if you're in a spin-4 manifold, this is related to earlier someone was asking about spheres, then you could just do this. Everything's even, run this table, do the disk embedding theorem, win. If this guy is allowed to be odd, then you get an actual invariant. And that prevents you from realizing your embedding by a sphere. But what we can do is change your surface into a torus and fix that last problem. Let's talk about that tomorrow. Thank you for your patience, Mark, and also everyone else. Thank you. I don't know if I'm allowed to do questions, you guys. Very big. Organizers?
Save them for the.
Yeah. Next talk is in 10 minutes. I will stand here for the next 5 minutes, and I will also attend the coffee session.